Hello everyone, and welcome to the lecture for section 5.2. So here we're going to look at graphing polynomial functions. This is a section of graphing polynomial functions. We're going to come back later in this chapter to do a bit more details, so you're going to see this in a couple of parts. So let's look at some problems. So in order to graph a polynomial function, we basically want to go through several steps. We want to find the behavior of the function at the endpoints, at the end behavior. That's for x goes to positive infinity or negative infinity. What is the function doing? So it could be doing two things. In the function itself, the y value could be going very large and positive, so it's going to positive infinity, or it goes large and negative. Okay, so you check at both ends for positive, large x values to see what the y value is doing. So it can either be going up towards positive infinity or down towards negative infinity. And then at the other end for x is large and negative, x going towards negative infinity. The y value could be going shoot up to the sky with y going to positive infinity, or go down to negative infinity. So that's the end behavior. Then we want to find some details in the middle. So what's happening in the middle of the polynomial? So we want to find things like y-intercepts. We also want to find the zeros of the function. And the real zero of the functions are the x-intercepts. We find the multiplicity of each real zero because that will tell us whether the function is crossing through that x-intercept. Is it crossing like a straight line, or is it crossing like an S? Or is it bouncing and coming up again, or bouncing and coming down again? So the multiplicity will tell you information like that. And we want more detail. We want to find the maximum number of turning points, just to kind of be aware of that, so we don't draw too many wiggles, basically. And then from that information we can do a good sketch. So it's not going to be like an exact graph, probably not as good as a parabola, but we can sort of do a very, very reasonable good sketch of a polynomial from all this information. Alright, so let's look at the first example. Alright, so we have this polynomial, it's in factored form. So all the ones that we're going to see in this section, they're either completely factored or as close to completely factored as possible. We might have to factor a little bit. In a later section, we're going to start with polynomials that are not in factored form, and those require a bit more work. Alright, so let's look at the end behavior. Alright, let's do that again. Okay. Alright. Make it a little bit bigger so we can see. Okay. So end behavior. So we see our function is factored. For the end behavior, we need the leading term. Alright. So the term with the highest exponent. Okay, so we could expand all this out and find all the terms, but that's not necessary. So to find the leading term, what you want to do is, let me write the function again, just so we can scribble things out. You want to look at each parentheses and keep the leading term in each parenthesis. So here, x plus 4, x has a higher power than 4, so we're going to scratch this out. Same for here, we have 1 minus x. X has a higher exponent, so we scratch this out. Okay, so what we get left with here is x squared in the first parentheses and negative x in the second, which gives me negative x cubed. So this is my leading term. Okay, so what this tells me is that at the ends, for x is plus or minus infinity, our function is going to behave like negative x cubed. So that like this power function and because the coefficient is negative, it's flipped over. Okay, so x cubed looks like this. This is what x cubed looks like. All right, negative x cubed is going to be reflected across the x-axis. So negative x cubed looks like this. Right? So we expect that at the ends, our function looks like going to positive infinity at this end and negative infinity at this end. All right? So that's what we need for end behavior, to figure out which way it's turning. All right, now let's find the y-intercept. So for y-intercept, we plug in x is 0, and we get 4 squared times 1, which is 16. So y-intercept is 0 and 16. Let's make that go up to 20. So 2, 4, 6, 8, 10, 12, 14, 16. So here's our y-intercept. All right, let's keep going. Find each 0 and its multiplicity. We'll use this information to determine whether function is touches or crosses at that point. Okay, so let's look back at our function, which is x plus 4 squared and 1 minus x. So we look at each factor and we set it equal to 0. So this gives me x equals negative 4. That's a real 0. And x equals 1. That's another real 0. Now the multiplicity of the first one is 2 because of this exponent. And the multiplicity of this one is 1 because it doesn't have an exponent there, means it's an exponent of 1. So this means that it touches at x equals negative 4, it crosses at x equals 1, it crosses like a line, right? So that's what a multiplicity of 1 tells you. All right. So let's graph the x-intercept. So I have, let's keep this as a 10. So let's go 1, 2, 3, 4. So that's a negative 4. And this is a 1. So a negative 4 is going to touch. So it's kind of, the function is up here above the x-axis for this portion. So it's going to come and touch and turn around. Right? And then it's going to go up to the 16. And then it has to come down at some point and cross here like a straight line. Okay, so that's what our zeros are telling us. All right, let's look at part D. So part D says, determine the maximum number of turning points. Right, so the maximum number of turning points is n minus 1, where n is the degree of the polynomial. So let's see, the degree of our polynomial is, it's of degree 3. All right, so this kind of going back to a, this is our leading coefficient. So this polynomial is degree 3. So that's our n. So n minus 1 is 2. So that means it has a maximum of 2 turning points. Okay. This is more like to make sure that you're not putting too many wiggles when you graph it. It's usually confirmed after you graph. You kind of go, oh yeah, look at that. It doesn't have any more than two turning points. Okay, so let's sketch a graph. So it starts up here. It goes to the x-axis and touch it at x equals negative 4. Turns around because that has a multiplicity of 2. Then it has to go through the 16 because that's the y-intercept. And it has to quickly turn around. Now it doesn't have to turn around at 16. It could go past and then turn around. This we don't know how to find. You need calculus for this. You don't really know how to find where the turning point is. But that is going to come really sharply and cross through x equals 1 and then go down towards infinity. Okay, so you're going to try to construct this function giving those pieces of information. This looks really awkward. My guess is that it's going to... polynomials are really nice and smooth. 2, 4, 6, 8, 10, 12, 14, 16. So here's 16. Let's try that again. My guess is going to go to the turning point and then come back and then come down like this. All right, that's my guess. So that's a sketch of the graph. All right, so guess what? We can verify by using a graphing utility. So I'm going to pull up Desmos. And great program. And put that function in. So the function is x plus 4 squared times 1 minus x. Right, so we put it in the box. All right, let's just make this a little bit smaller so we can see the whole picture. All right, and we can zoom out. Okay, so we can see that at -4, it touches and turns. This starts with positive infinity. It touches and turns at -4. It goes up and then down to the 16, and then it crosses through at -1, and then it goes, y value goes down to negative infinity. Okay, so you can see the behavior of this graph is as we sketched it on paper. Right. Desmos is a great tool to verify. I want you to learn sort of all the methods by hand, finding all the things we did by hand, but definitely you can use Desmos to verify your findings. All right, let's move on to the next problem. So this example here. So we're going to start with a different polynomial, go through the same steps. All right, and ultimately we want to get a sketch of it. All right, so part A, we want to determine the end behavior. So again, let's find the leading term first. So I'm going to look at, we have -2, x minus 1 squared, x squared minus 16. All right, so let's get rid of the lower terms in each parentheses. And we have -2 x squared, which is -2x to the 4. Okay, so this at the ends behaves like -2x to the 4. Okay, so x to the 4 is like a fat parabola. This is x to the 4. -2x to the 4 is going to be upside down. Okay, so you can see that the end behavior is that it's going to negative infinity at both ends. Okay. So when I graph it, I'm expecting it to look like this at the ends. All right, let's find the y-intercept. So part B, the y-intercept is when I plug in x is 0. So I have -2, -1 squared, -16. So we have -2 times +1 times -16, which is +32. So my y-intercept is at 0 and 32. All right, let's make this, let's go by 5s. 5, 10, 15, 20, 25, 30, 35, 40. All right, so let's make that scale. So our y-intercept is at 32. So we're around here somewhere. All right, now we need the zeros and their multiplicity. Okay, so let's rewrite the function. f of x equals -2, x minus 1 squared, x squared minus 16. Notice that this is not completely factored because this could be factored more. So we're going to do that. Okay, so we have negative 2x minus 1 squared, x minus 4, and x plus 4. Alright, so to figure out the proper multiplicity for each root, for each zero, you need it to be completely factored. So we get x equals 1 from that factor, and it has a multiplicity of 2. We get x equals 4, that has a multiplicity of 1. And x equals negative 4 with a multiplicity of 1. Okay? So this one, it touches, and this it crosses, and this one is crosses. Alright, let's look at part D. Determine the maximum number of turning points. So there's n minus 1 turning points. Our n is the degree of the highest term. So this is 4 minus 1, which is 3. So this is the maximum number of turning points. Alright, let's sketch this. Okay, so we have our n behavior on the graph. We have our y-intercept. We're going to draw our x-intercepts. So we have one at negative 4. 1, 2, 3, 4. We have one at positive 4. 1, 2, 3, 4. And we have one at x equals 1. Alright, so I'm going to sort of redraw the ends so it kind of fits with this. So it's going to cross at 4 and negative 4. So it starts down here, it goes and crosses through negative 4. Right. Then somehow it needs to go through 32. I'm not sure where. We could go past it and then back down. Then at x equals 1 is going to touch. So here we need to get close to here and then touch and turn around. And then it's going to cross through 4 and then needs to end down here. So we're going to cross through and then, this is really bad wiggles. Let's try again. Cross through and then go down here. Okay. Now I don't know how high this ends in. I'm just guessing. It could have gone higher. This could have gone past and then higher. That behavior you need calculus for. So you can, if you're taking calculus next, big part of it is finding where these turning points are. All right, let's verify with Desmos. Let's see, can I find my Desmos window? It's behind here somewhere. All right, so we want to graph this function and see if it looks out like our graph. All right. I'm trying to fit everything in one place. Okay, so let's do, it's negative 2 times x minus 1 squared, and then x squared minus 16. I just typed in the original one. You could have factored typed in the factored form. All right, here's what we're getting. Let me, yeah, it's hard to see, right? So let me set the scale of this with x from negative 10 to 10. All right, so you can see that it's going through negative 4. It shoots up to this this turning point, then goes through 32 as the y-intercept. It touches and turns at x equals 1. Then it goes up and has to turn around so it can pass through positive 4 and then go down to negative infinity. So the general shape is like the one here. The scale is way off because I didn't know that it was going to go like way much higher and then turn back. All right, as I said, you can't really find those things yet, right? Okay, let's look at the next example. So we're going to graph the polynomial function, again, following all the steps. So let's find the end behavior first. Right, so let's say a here. We're going to go to our function and erase the lower terms. Okay, so we have x squared, x minus 2, x squared plus 3. Let's cross out the lower terms in each parenthesis. So we get x squared times x squared gives me x to the 5. So positive x to the 5. So at the endpoints, the end behavior, this function looks like an x to the 5, which is something like this. Looks like a cubic, but just a bit steeper. Yeah? So that means that I know that it's starts at negative infinity here. It's going to do some stuff, have some intercepts and some turning points, and then go up here. Alright, let's look at B. We're going to find the y-intercept. F at 0 is 0 times negative 2 times 3, which is equal to 0. So our y-intercept is at 0, 0. Okay, so this is passing through the origin. So it means it's also an x-intercept. Okay, let's look at each 0 and the multiplicity. So I'm going to write the function again so we can look at it a little bit closer. Alright, so I look at this, and this is as factored as I can do it, because this last factor has a square in it, but because this is a plus, it doesn't factor as a difference of squares. So this does not give me any real zeros. So we don't get any x-intercepts from here. So that's not going to be, this doesn't generate any x-intercepts. Okay? So we look at this term. So the solution of that is x is 0. And it has a multiplicity of 2 because it's squared. This one gives me x equals 2, and it has a multiplicity of 1. So this one touches, this one crosses, and this does not give me a intercept. So we ignore it when it comes to the zeros. Let's look at the number of turning points. So D. We saw earlier that our function looks like x to the 5, so this is the leading term. So the degree equals to 5, so n minus 1 equals 4. So it's 4 maximum turning points. Alright, let's try to sketch this. So let's go back to our zeros. So x is 0, multiplicity of 2, so there's a touch and turn, right? And then at x equals to 2, there's a 0, but it crosses through. Okay? So let's see what we can do. So start down here, we go up, we touch and we turn. Then we have to cross through here, so we got to turn again and then go through. Yeah. So this is what it might look like. Again, this method is a bit limited because this is, I have a maximum of 4 turning points. In my graph, there's only 2, which could completely be correct because 2 is lower than 4. But it's possible that I can get a different graph for this. It's possible that my graph looks like something like this, right? So it has like more wiggles in it. 1, 2, 3, 4 turning points. We don't really know with sort of doing this method. To figure out how many, we'd have to do a bit of calculus to figure out how many turning points, right? So let's verify with Desmos. Let's see what Desmos says. Okay, so we're going to have x squared x minus 2, x squared plus 3, So it looks like our first version was good. Alright, so let me change the scale a little bit. Make the y values from -10 to 10. Alright, so up, touch, turn back, and cross through x equals to 2. Okay? So the red version was the correct one. Now, when you do these, it's going to ask you for things like give a possible graph for this. So it's understood that there could be more than one version with the material, with the knowledge that you have right now, and the details will come later. Okay, so either one that you give me would be correct with what you know right now. Good. That's it for the section. We're going to talk more about zeros of polynomials in the later section. We're going to start with a function not in factored form and try to get it there, try to figure out what the zeros and the x-intercepts are if it's not already factored. All right, see you in the next section.